All right, welcome everyone to the second week of this 2D workshop. So a lot of new participants, so welcome to all of you. And I'm Arun Paramekanti, I'm one of the co-organizers and will be chairing the session. So we have two talks in the session. And the first talk by Abhay Pasupathy and the second by Manish Jain. So before we begin, I just had a quick announcement. So during the afternoon tea break, there'll be a photograph taken for the conference photograph. More details, I think, will be given by, I think one of the other organizers is in charge, so they'll kind of tell you more about it probably in the session after lunch. So without further delay, let's begin. So with the first talk by Abhay Pasupathy from Colombia.
Okay, thanks, Arun. Thank you to you and the other organizers for having me here. It's always a pleasure to be back in my hometown. And today it's not raining, so that's good. Hey, Shahal, I see you so many times this summer. Okay. So for those of you who don't know me, I primarily work at Columbia University, but I have a second master to pay the bills, which is Brookhaven National Lab. Okay, I'm going to tell you about work that we've been working on for about 5 years, which is, I hope fits within the theme of this conference. It's at engineered quantum systems. And this is very much engineered after a certain way, two layers of twisted tungsten diselenide. Tungsten diselenide is a famous monolayer semiconductor. Let me first start by acknowledging the people who did this work. So this work was actually started by one of my graduate students who's now moved on, Augusto. And it's an interesting case of why one should go to a conference and hear random things. So the way we got into this was sometime late in 2018, we went to a conference. This was shortly after the twisted bilayer graphene, and Pablo was there and Philip Kim and other people. And I was talking to Philip, and I said, Philip, what are you doing in this field? And Philip said, well, we are measuring twisted WSe2. And I said, well, did you find anything interesting? He said, well, it seems to be a superconductor. And I asked him, oh, well, what's TC? He said, maybe 10 Kelvin, maybe 1 Kelvin. I said, what is this? And Augusto was standing next to me, and he said, this sounds very suspicious. I'm going to go home and start making these samples. Okay, so that's how he got into it. It turned out to be a complete rumor. None of Philip's samples are superconducting. In fact, right now I'll show you some evidence for superconductivity, which is actually very recent. Anyway, so the way Augusto got into it was he gathered a student from Corey Dean's lab. This is N Min, who's also moved on now. So Augusto at the time was not very good with all of this tearing and all of this stuff, which is now very popular. But there was a postdoc who was a joint postdoc in our Morsec Center, Lei Wang, who's also now moved on. And Augusto sort of grabbed these two guys, N Min and Lei. And the first set of work was sort of the three of them. Since then, there's sort of more recent work, people from my group, Larry and Aya. I'll also talk most recently about superconductivity work, which happened sort of by accident. This is one of Corey Dean's students, Inji. And I work very closely with Corey and Jim Hone. They are the people who teach me all this 2D stuff. And then there's hexagonal boron nitride, of course. I'm sure many of you know these friends of everybody. And then a lot of theory, especially Andy Millis and his group, but also Angel Rubio and his group. Okay, so let me tell you, I assume you might have heard some of this earlier in the conference, or I'm sure earlier before. This is sort of a popular field. But let me get to the basic physics of what it is that we're trying to do. We are trying to create systems where we quench the kinetic energy of the electrons. And so the basic idea is very old, goes back to many different systems. The idea is you take a free particle, which has some quadratic dispersion in 2 dimensions. This has a flat density of states. And you apply a superlattice potential. The superlattice potential has some periodicity in real space and some periodicity in reciprocal space. And that breaks up this original band, which has a large bandwidth, into little mini bands, and these little mini bands can have an arbitrarily small bandwidth depending upon how big you make this superlattice. Now, for practical reasons, you want the bandwidth of this superlattice to be not too small. If it's too small and you have disorder in your system, then you can have all kinds of localization effects. So you want it, in the case of TMDs, to be on the order of tens of MeV. And if you work that out into real space and ask what the superlattice potential should be, it should be on the order of 5 to 10 nanometers. That's the typical length scale we're talking about. Okay, and the way this is done, this goes back to, I believe, Emmanuel, who's right there, who came up with this very clever way of doing business, which is to take a sheet, which is a two-dimensional material, tear it into two pieces, twist one relative to the other, and put it on top of each other. This is called the tear and stack method. And there have been many sort of iterations of this over the years since, I think, now 2015, that's when he first did it. But the same basic idea is applied in each case. And all the physics that I'm going to tell you about refers to the case where the chemical potential is within this lowest subband. So the chemical potential is lying somewhere within this guy. And so for all practical purposes, you can ignore a lot of these other subbands which lie at higher energy. And you can imagine what life is like in a single spinful, in the case of WSe2, single spinful subband, which you can control the doping, and you can also control the bandwidth, as I'll explain in just a second. And for almost everything, this kind of description is reasonable. Of course, if you're dealing with topological properties, then you have to worry about multiple bands. But in this talk, I'll not be discussing any topology. And in this system is actually a really nice platform for engineering. So you can do many different things to tune this system. So simplest thing you can do is you can choose different types of materials. The material I'll talk about is twisted tungsten diselenide. But there's work on tungsten diselenide, on tungsten disulfide. There's tungsten diselenide on molytelluride, molytelluride on molytelluride. And if you've been following this field, there have been sort of many beautiful experimental discoveries over the past few years, Wigner crystals, the anomalous integer quantum Hall effect, and most recently, the anomalous fractional quantum Hall effect. All of these things have been discovered in this materials platform. Now, once you've picked a particular material, you still have a lot of tuning parameters that you can play with. You can play with the twist angle. So the twist angle sets the wavelength of the superlattice in real space. And the smaller the twist angle, the larger the wavelength in real space, and the smaller the wavelength in reciprocal space. You also have two gates in all of these devices. So if you have a bilayer, you can put a gate on top and a gate on the bottom. If you apply the same voltage to both the gates, then you tune the density of electrons on this. And if you apply equal and opposite voltages to the two gates, then you end up applying just an electric field. And as I'll show you, the electric field in our system controls the bandwidth of the system. Okay? And finally, one thing that we've sort of by accident gotten to recently is you can also control dielectric screening in this system. So you have a bilayer system, and the bilayer system is close to a gate. And if you bring this gate very, very close to the bilayer system, then effectively you screen the long-range part of the Coulomb interaction. So this is another degree of freedom that you can play with. Okay, so I'll keep an eye on time. I'll make sure I won't go late. But I wanted to sort of review all of the work that we've been doing since our original work. So I'll talk about 1, 2, 3, 4, 5 different things. Out of these 5 things, I'll try to be fairly quick about 1, 2, and 3, these first 3 things. This is sort of in the nature of background. And I'll try to spend a little bit more time on the most recent results, which is from this year. Okay, okay, so let's start with the first part of the story, which is what happens when you make the sample. What's the most obvious thing that you see in these samples? And I should also mention that these particular samples are made at a twist angle that's anywhere between 4 and 5 degrees. If you're interested in what happens at smaller twist angles, I can talk about it later, but let's ignore that for now. Okay, so let's start with the very basic picture. How do I understand the electronic structure, the band structure of twisted WSe2? So if I take one layer of WSe2, it is a triangular lattice in real space. So here's the reciprocal space version of this. It has, if you're close to the band edge, then its contours of constant energy look like circles, which are centered around the K point, similar to graphene. And if I have 2 of these layers, and these 2 layers are misaligned with respect to each other by some angle, then I have 2 of these bands in reciprocal space, which are also rotated with respect to each other by the same angle. And so if I take a cut through, for example, this line, which goes between two of these circles, then I'll see something that looks like this. I see a conduction band and a conduction band from the two layers, which are offset from each other because of the twist angle. And one of these is around the K point, and one of these is around the K prime point. And also, I'll see a valence band for both of them. Now, of course, the way this is drawn makes it look like the gap is small. The gap in these systems is actually enormous. It's on the order of 1.5 or more eV. And so effectively, we work either in the valence band or in the conduction band. And for the case of WSe2, it's easiest to work in the valence band because that's where you can make nice devices. So all of the physics that I'm going to tell you about is essentially occurring in this top part of the valence band. And all you need to worry about is the very top of the valence band, which kind of looks like that. Okay, so when we made our first set of samples and we measured them, this was sort of the transport data that we measured. And what I'm showing you here is a longitudinal resistance of a sample as a function of doping. So doping here is on this axis. And 0 here is the valence band edge. Near the valence band edge, you see insulating behavior. This is just because it's a crappy semiconductor when you're close to the edge of the valence band. And as you start doping, you start seeing conduction. And if you take a sample that has two layers which are aligned with each other, natural alignment, this is a so-called Bernal stacking, the conductivity of the sample just keeps increasing as you pump more and more carriers into it, and it just becomes a good metal as you dope it more and more. On the other hand, if you choose a sample which has a twist in it, so this is 4 and various different angles, you notice something interesting. You notice that there's a peak in the resistance, and this peak turns out to be an insulating peak. If you measure the temperature dependence, this turns out to be an insulating state. And this insulating state, if you work out the numbers, you will find out that it occurs precisely at half filling of this lowest subband. Okay? And the reason that it occurs at different values of density is because as you change the twist angle, you change the size of the unit cell, and therefore the absolute density that you require to reach the half filling condition changes. Okay, now one very interesting thing that we found, which in retrospect is fairly obvious, is the effect of an electric field. So an electric field is if I apply a field that is perpendicular to these two layers, this can actually tune the bandwidth of this band. And the easy way to see this is the following. So let's go to that picture that I showed you earlier and zoom in just to the top of the valence band. So this is the valence band from one layer. This is the valence band from the other layer. And if I apply this electric field, then the two layers have different electrostatic potentials because I have integral E dot dl. And what this means is that the valence band from the top layer is going to go up and the valence band from the bottom layer is going to go down. And then if I work out what happens in a more systematic way, this is with DFT, you can see that when I start to apply electric fields, you see this effect. You see one of these bands go up and the other band go down. And this therefore tunes the bandwidth of the system. And also a very important detail that I'll come back to several times in this talk and you should pay attention to is if I look at this particular band structure, there's a particular point right there. This point is a saddle point in the band structure. It's a Van Hoff singularity. If I go in this direction, you see that it has a curvature up. If I go in the other direction, it will have a curvature down. And it's therefore a peak in the density of states. This peak in the density of states occurs somewhere between the top of the band and the bottom of the band. And as I apply this electric field, I can tune where this Van Hoff singularity lies by just changing the value of the electric field. And this is a very important thing. Okay, so what we did is we measured as a function of density. Density is on the x-axis, and the electric field is on the y-axis. And we measured around this half-filling point for a range of samples. And what we saw is that for a range of samples, you see insulating behavior. And this insulating behavior lives in a little pocket that is right around half-filling. Okay? And so that's sort of the picture of the band. I've half-filled this band, and when I have a half-filled band, I have an insulating state instead of a metallic state. So this was sort of the first finding. The way we rationalized where in this phase diagram of electric field and density the insulating state appears is by looking at the value of the density of states. And what we found is if you look at theory and ask yourself where is the density of states maximum, in other words, where is that Van Hoff singularity close to half filling as a function of twist angle and as a function of electric field, then we find that it is indeed maximized in this range of angles and at some range of electric fields. And that's indeed around the place where we see insulating behavior. So the picture that emerged from this first work is that we are in a regime of moderate correlations where the density of states helps us enter into some broken symmetry phase, and this broken symmetry phase has a gap in it. Okay, so now I'm going to go very quickly into the second part of the story, and I'm going to be very brief because this is theory. So this is theory from Andy Millis and his collaborators. And I should say that this is Hartree-Fock theory. And I should also say that there have been many, many works done which I'm not referencing here. And if you're one of the authors who've done one of those, I apologize in advance. What Andy said, and this basic point is something that I want to reiterate, is if you look generically, you will find that there are many different types of broken symmetry phases that are possible in this system. And in general, this is always true because there is a Van Hove singularity in the system. And whenever you're close to a Van Hove singularity, in Hartree-Fock theory, you'll very often find these kinds of broken symmetry phases. I don't mean to convey a whole lot from this other than to say that all of these phases are magnetic in some type or the other. So there's various types of antiferromagnetic phases. Here's a stripe phase. Here's a 120-degree Néel phase. There's also ferromagnetic phases, and so on and so forth. And the general picture at this level of theory is that as you change doping and you approach this half-filling point, here is the half-filling point, you first have a transition into a metallic magnetic state with this kind of symmetry breaking. And then as you crank up the strength of that order parameter, you can eventually enter an insulator with magnetic order. And then as you go through half filling and go out the other side, you still have some metallic magnet until eventually you go over into a paramagnetic phase. Okay, so yeah, so I already said this. And the basic physics of this is basically the physics of a Stoner instability in a ferromagnet, right? So in a ferromagnet, you know that it's not just the strength of the interaction that matters, but it's the strength of the interaction times the density of states that matters. And something very similar would happen with all kinds of density wave orders. And so the basic idea is as you approach the Van Hove singularity, you have some strong nesting towards some type of order, and this gives you an ordered phase, some kind of density wave order. No, both values participate. In the order you Yes, yeah. Okay, yes, please. So it's of order tens of millivolts, maybe up to 100 millivolts. Yeah, so the bandwidth is also on the order of 50 millivolts. So yes, if you're to do something serious, then you should take higher order subbands into account and longer range interactions also into account. Okay, so now in our experiment, at least in our first experiment, we could not see any evidence for this metallic magnetic state. What we saw was evidence for an insulating state, but of course we don't know whether it's magnetic or not. So we started looking more carefully at what happens as you go near the boundaries of this insulating phase. And one of the interesting things that we found that's in the second work is, I'm just drawing here in a cartoon form, this is where that insulating phase is located as a function of electric field and as a function of density. This is for two different angles. And you can go and look at the behavior of the sample by measuring its resistance as a function of temperature and figure out whether the sample is insulating or metallic. And you can also measure the size of the gap from an Arrhenius fit. And if you plot that as a function of electric field, that's the blue line, or as a function of density, that's this purple line, and you measure the gap as you cross this ring, what you notice is that the gap goes continuously to 0. Right? And this gives some sort of, what can I say, some support for the idea that you have a continuous phase transition as you go from here from this insulating phase to this metallic phase. And it sort of fits in with the theory that there is some magnetic order that's on this side and on this side, and the gap eventually opens when that order is strong enough. But of course, again, here, we are not directly measuring magnetism in any way. And it turns out that if you measure transport signatures in the vicinity of this kind of critical point, you indeed measure lots of interesting and fun properties. For example, there's a region of T-linear behavior, and so on and so forth. All of that is interesting, but directly by measuring the transport in this kind of region, it's difficult to tell if I have a magnetic phase that's present or not. Okay? So, please. As against a Mott insulator. So, you know, I'm measuring transport, so I can tell you it's an insulator. Anything beyond that is theory. Okay, so with this now, let me go to the, yeah. Yeah, what is the best evidence for that is, so certainly we have samples which are more inhomogeneous, and there you kind of see insulating behavior at random points in the phase diagram. So this is always pinned to half filling. Is disorder important? I'm sure disorder is important, right? You know, the best we can say is experimentally we see it for a range of samples, range of dopings, et cetera, but we don't have a very good quantification of what the strength of disorder is at this point. And this is true in all experiments in this field. Okay, so the next part, which I'm going to spend a little bit more time on, is we wanted to track down this idea that there could be some magnetic order present in the system, even when it's a metal. And so I'll show you some transport evidence for this. So I'm showing you a sort of different sample, but very similar. This is 4.2 degrees. Once again, here I'm plotting the, this is the Hall resistance. Okay, the Hall resistance as a function of electric field and doping. And we have this bad habit of putting 1 here sometimes and half here sometimes. This is half filling. So depending on how you count, sometimes this is half and sometimes this is 1. But the insulating phase in this particular sample is located around here. And what I'm going to show you are data that's taken away from the insulating phase. So in particular, I'm going to show you data that's taken along a cut that goes in this particular direction. And nowhere along this cut is a sample an insulator. The sample is always a metal. And what I want to show you are transport data and convince you that this kind of interesting behavior that you see here is associated with a magnetic metal. Okay? And so here are a set of these data. And what these data are is as a function of magnetic field. The magnetic field is along the y-axis. And one of the gate voltages that I use to tune the density, that's along the x-axis. And the band edge is somewhere around here. And this is tuning the density. And half filling, now I've gone to the -1 notation, half filling is right there. If you look at half filling in this particular sample, there is no hint of an insulator whatsoever. But I hope all of you see that there's some interesting behavior that happens right around here, something that I want to talk about. And this is done for one value of electric field. This is done for a different value of electric field. And finally, if I tune the electric field just right till I reach that insulating phase, at this particular value of the electric field, I've hit that insulating phase. You can see that insulating phase, which appears precisely at half filling. But at these values of electric field, there is no insulating phase at half filling. And I want to talk to you about what the magnetotransport looks like at these values of electric field. Okay, so, and I'm going to concentrate primarily on the Hall effect. And so this is the longitudinal resistivity. If I plot for you the Hall effect looks complicated. So here you can see all kinds of different colors. And the colors here, red color here is a positive Hall coefficient, and blue color here is a negative Hall coefficient. Okay, so let me walk you through this a little bit and try to convince you that there's something interesting. Okay, so let's first take the theoretical band structure. So this is the theoretical single particle band structure. and ask ourselves, what should the Hall effect be if I just take non-interacting electrons, put them in a band that looks like this, and measure the Hall effect? What should the Hall effect be? Well, our textbook tells us that the Hall effect goes as 1 over the density. And here, when I'm close to the edge of the band, I have a hole pocket, and I have a hole pocket, hole pocket, hole pocket. The hole pocket is getting bigger and bigger, which means the Hall resistance is getting smaller and smaller in sort of a 1 over n fashion until I hit this Van Hove singularity. And when I hit this Van Hove singularity, I should go from holes to electrons. And so I should have a sign change of the Hall effect. And then I have electrons, and then electrons, 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 all the way till I reach the end of the band, where once again, I have a large Hall coefficient. Okay, so this is the theoretical expectation for what one should have. Let's look at experiment and see what experiment says along this same region of density. So if I'm somewhere here, far away from this Van Hove singularity, I measure the Hall coefficient, and you look at low fields, ignore what happens at high fields. You see, indeed, it has a nice linear behavior. You can extract a density from this, and you can put it onto that, and it works out pretty well. Within a few percent, it hits where it should be. Now, I come closer, you see that the slope of this thing changes, but the same thing. But now I come pretty close to the Van Hove singularity, and you see something quite different happens. So now if I look at the Hall effect indeed has that same slope at low field, but if I go over to higher field, you see that the sign of the Hall coefficient changes. And this is very common in a system that has multiple bands. You'll see this kind of behavior. And now if I go sufficiently far on the other side, this behavior starts to disappear, and eventually I get an electron band, as I should. So close to the Van Hove singularity, the Hall coefficient deviates from the single particle expectation. And if I plot the low field Hall coefficient as a function of density, you can see quite beautifully that if I'm far from the Van Hove singularity, so the Van Hove singularity here is at minus 1.1 roughly. If I'm far from this point, I have more or less the non-interacting expectation on the hole side and on the electron side. But if I'm close to the Van Hove singularity, I have this gigantic peak. And this is our primary evidence that you have a Fermi surface reconstruction in this particular system. And this is just sort of putting all of the data together. You can see the nice evolution from the hole side to the electron side, and in between this interesting behavior. You can try to track down and see whether there's evidence that this is a real phase transition. So what you can do is you can apply higher temperature. So this is higher temperature, and you can also look at as a function of magnetic field. As a function of temperature, this behavior disappears by around 30 Kelvin. And so our evidence that this is a real phase is from this sort of behavior. If you go to high enough temperature, all of this behavior disappears, and it more or less matches the non-interacting expectation. And if you apply a magnetic field, then with a reasonable magnetic field, again, you can quench this behavior, which is our evidence that this is somehow a magnetic phase. Okay? And let me just tell you what we think this is. We think this is 120-degree Néel order. This seems to be the most likely thing. When you're close to the Van Hove singularity, this kind of order sets in. And here's sort of some calculations from Andy and collaborators for what happens when you have this kind of magnetic order that sets in. I hope that's not me. Okay. So this is the band structure before the reconstruction. There's the Van Hove singularity. And if you put your chemical potential in the vicinity of this Van Hove singularity, then you have a Fermi surface reconstruction. When you have this Fermi surface reconstruction, you can see that there's both hole and electron pockets, and that changes the Hall coefficient, as one should expect. And we can sort of make a reasonable picture for how Fermi surfaces evolve and all this sort of stuff. I should stress that all of these things are just theory. We don't measure these things in theory, in experiment as of now. But our evidence for all of this is from the Hall effect. Okay, very good. So with this, I'm going to go to my final topic, which is superconductivity. And this actually is fairly recent work from this year. And Inji was making a sample which she wanted to make at 4 degrees to follow up on some of these measurements. Unfortunately, when she made the sample, it turned out to be 5 degrees instead of 4 degrees. This happens from time to time. But Inji, being a diligent student, stuck it and measured it. And she measured it for a while and found nothing interesting. And we were thinking of throwing the sample away. And she said, no, I'm going to measure it in the dilution fridge. And she stuck it in the dilution fridge, and hey presto, the sample became superconducting. Okay, so that's this story. Now, again, I'm going to start with the phase diagram. So this is density along this axis, and this is electric field along this axis. And I'm going to show you first the longitudinal resistance. So this is longitudinal resistance on this phase diagram, as well as the transverse or Hall resistance that's shown here. And there are many things going on here, which I'll clarify later, but I want to give you a few markers for what various things are. The first and perhaps most important thing you should notice is that if I sit at 0 electric field, and if I sit at half filling, so -1 is right there, and I measure the resistance as a function of filling, then you'll see that this particular sample has no insulating phase whatsoever. Right? In fact, it has no insulating phase anywhere until you get very close to the band edge and you have disorder. The second thing I hope you can see, all of you, is that this dashed line, which is drawn in a schematic here, you can see a faint thing in Rxx. And even better, if you look at Rxy, you need to think about this a little bit, but you can see a sign change of Rxy that happens right here. That's the white region. And that's once again the Van Hove singularity. Right? So here's the Van Hove singularity line. And if I sit at 0 electric field, the Van Hove singularity is here. And if I tune the electric field, as I told you earlier, I can tune where this Van Hove singularity lives in the band. And so this line has some curved shape that looks like this, goes like this. Okay. For those of you who have been following this work for a little while, I do want to say something. If you've not been following it, don't worry about what I say next. In our very first work in 2020, we had measured a sample that was very close to this 5.1 degrees. And in that sample, we did see an insulating phase. Right? And if you ask me what's different between this sample and that sample, one thing that's very different in this sample is that in this new sample, for whatever reason, I don't know what was going on in Inji's head, she made the dielectric thickness very thin. She made it 5 nanometers, which is much thinner than the dielectric thickness that was used in the previous sample. Okay? So in the previous sample, we had a thicker dielectric. We did see an insulating phase. If you read our paper carefully, we claim to see superconductivity near the edge of the insulating phase, but the referees made us retract that statement because we didn't have enough evidence at the time. So we stuck it in there and kind of buried it in the paper. But exactly at the same place in the phase diagram, we see superconductivity, again, now much more clearly. But the difference between the new sample and the old sample is that the new sample does not have this insulating phase anywhere. And it's possibly because the dielectric thickness is thinner, so screening is better. Okay, but let me now concentrate on this part of the phase diagram as a function of electric field and density. And in particular, this little dark blue thing here, that is superconductivity. Okay. So zooming in right there, this pocket here, this pocket is 0 resistance. And I hope all of you see that around this pocket, you have something interesting going on. And just to show you some line cuts, that if you're sitting here and you measure resistance as a function of temperature, you indeed see a superconducting transition. The maximum TC we see is around half a Kelvin, so it's not going to impress anybody as a superconductor, but still it is a superconductor. And if you go away from this point, then you see normal state if you go somewhere away. And I have to say that we have not characterized the normal state particularly well. So if you're interested in knowing whether the behavior is still linear and so on, we don't have great data on this just yet. Okay, so just to show you a few characteristics of superconductivity, you can see that there is a critical current. You also measured Fraunhofer patterns in this. You can measure the magnetic field dependence. So very modest magnetic field, few tens of millitesla suppresses this. So all good things for a superconductor. You can calculate a coherence length and a mean free path. And what you'll find is that this ratio, if you just do this from the magnetic field, is about a quarter. Okay, so now the most interesting thing, as far as I'm concerned, is to ask what is this thing that is immediately adjacent to the superconductor? And one way we can study these things, there are two ways we can do this. One is we can raise the temperature till we are in the normal state, or we can apply a small magnetic field till we are in the normal state. and then look at this particular region of phase space and ask what does the resistance look like. And here this is done at a small magnetic field. If you apply a small magnetic field, you see very clearly that there's this little region here that's interesting and looks different from the region around it, right? And this has precisely the same phenomenology that I was talking about earlier of having a Fermi surface reconstruction. So we believe that this particular thing that is adjacent to the superconducting phase is indeed an antiferromagnetic metal phase. And let me just show you some of the transport data in that region. If you measure the Hall effect, once again, you see this very nonlinear Hall effect, just like I showed you before. I'm not showing you data at densities that are far away. That looks exactly the same as the previous samples. If you look at the longitudinal magnetoresistance, this also shows these interesting signatures that go along with the same field scales. So everything here in this particular sample points to the fact that we have an antiferromagnetic state that's right there in the vicinity of the superconducting phase. So if you put all of this together, this is sort of the phase diagram that you get, that there is some antiferromagnetic metal. And I have to confess that transport is not the best way to tell you what really the boundaries of this antiferromagnetic metal are. And so I cannot tell you if it ends abruptly here or if it goes a little further there. That's difficult to tell. But what we can clearly see is that there's some boundary between this phase and the superconducting phase, which is very sharp. We can watch the evolution of that boundary as a function of temperature. So here are data taken at a set of different temperatures from 30 millikelvin to above TC, the highest TC. And what you see is you see this arrowhead-like shape. And the shape of this arrowhead, the size of this arrowhead keeps shrinking as I increase the temperature. But I hope all of you see that this particular boundary here, this boundary here, remains reasonably sharp all the way up to 400 millikelvin. But the other boundary that's down here, it disappears in a continuous fashion. And so if you ask me what's going on with superconductivity, if I was to measure TC at different points, I would tell you that TC continuously drops to 0 as I go down this particular way. But TC, there's some sharp jump of TC as I go from here to the other side. Yeah, so straight boundaries of the antiferromagnet and curved boundaries of the metal. And this is sort of a contour plot of where superconductivity lives at different temperatures, telling you essentially the same thing. If you go across this boundary, so if you're very close to this boundary between the superconductor and the antiferromagnet, what you very often see is you see the remnant of a transition, but then it goes to a non-zero resistance at low temperature. And this could be a signature of perhaps phase coexistence. That's possible. Could be other reasons too. But you see that there's still a fairly sharp superconducting transition and then non-zero resistance if you're very close to this boundary. We can do a little bit more. So what I can do is I can go along this particular line and I can plot the resistance as a function of density. And I can sweep back and forth to look for any signs of hysteresis. And we see small signs of hysteresis. So it depends on how kind you want to be to us. But certainly this is reproducible. You see some hysteresis a little bit on this particular boundary, whereas at this particular boundary, we cannot see anything at all. And this kind of hysteresis has been seen both in bilayer graphene by Andrea Young and by Mandar Deshmukh's group in twisted trilayer graphene. Okay, so what's a plausible scenario? So what we know for sure is both this magnetism or this Fermi surface reconstruction and superconductivity lie near the Van Hove singularity where the density of states is high. That's kind of obvious in all situations. And now one can ask, if this superconductivity is phonon driven, then why does the superconductivity have to lie there? Why could it not lie there? There's a Van Hove singularity here and a Van Hove singularity everywhere along this line. Why does it decide to live near the magnetic state? Could be it's a pure accident. This is a place where the density of states is maximized, and it's good for superconductivity in whatever mechanism. But there's sort of a more natural and tantalizing explanation is that this superconductivity is somehow related to the destabilization of magnetic order. So it's mediated by magnetic fluctuations. But this is a speculation at this point. What we know for an experimental fact is that these two phases basically live right next to each other and only in that region. Okay, so that's all basically I had to say. I think I'm good on time. And I'm just going to put up all of the things that I wanted to say right there and conclude. And thank you.
Time for questions.
Hi, Abhay. So what's the evidence that it's an antiferromagnetic versus any other magnetic ordered metal? Do you see it in transport?
Yeah, so certainly it's not a ferromagnet. So we see no hysteresis. And there have been some optical measurements which would have seen ferromagnetism if there was ferromagnetism. At lower twist angles, you do see ferromagnetism appear. So ferromagnet phases are not far away from this. And Xiaodong has some data on ferromagnetism at lower twist angles. But at these twist angles, there's no evidence of ferromagnetism from optics. And there's no hysteresis seen in transport. Now, ferromagnetism by itself, it would do something different to the Hall effect. But this sort of simple picture of the Fermi surface reconstruction would not be the same in a ferromagnet. So it's all circumstantial from the perspective of transport. The only concrete thing is we don't see any hysteresis in transport.
Can it be a fluctuating moment phase like Andrea, like in magic angle graphene and now in Bernal bilayer graphene is seen?
Yeah, I don't know enough about that. So the question would be whether that kind of fluctuating phase is sufficient to have a strong signature in the Hall effect. I don't know.
Thank you. Can you rule out coexistence of antiferromagnetism and superconductivity? You sort of implied that there was some first order like transition and there wasn't coexistence.
Yeah, we cannot. So all we have are transport data. It's entirely possible that even when you're well within the superconducting phase, that the sample has antiferromagnetism at a higher temperature and then is superconducting at lower temperature. That's entirely possible. We don't have any evidence one way or the other.
So you're saying at the moment there's no real method to measure in the superconducting phase to see if it's still antiferromagnetic?
That's right. So we can measure just from transport the regular signatures of superconductivity in transport, but to tell that it's also an antiferromagnet, that requires a little bit more work, I think.
Yeah. I was interested to know if you measured the volume fraction, the superconducting volume fraction, say through Meissner-like response or something, a diamagnetic screening response.
So far, none of those things are directly possible. These are all just transport, so we can tell basically resistive signatures. So it's feasible to do this with NVs, for example. But it's not an easy experiment. The volume is nothing.
Okay.
Yeah.
And I also wanted to know that in this superconducting phase, if you apply a strong magnetic field and you suppress the superconducting state, do you see any antiferromagnetic fluctuations persisting in the normal state in that region, or?
Yeah, so that was one of the slides I flashed, that if you go to 100 millitesla where superconductivity is suppressed, and you look at the phenomenology, you see evidence in the Hall effect for this Fermi surface reconstruction. Okay. And so, yes, indeed, we do think so.
I see. Thank you.
Okay, so
there's a question back there. Arun, there's one back there.
Yeah, so I have a question related to the first question. So you see there is a change in the slope of Hall, and you tell it because of its multiband. But does that tell that really antiferromagnetism is there from Hall data?
No, all it tells you is that if you take the data literally, that it's a multiband, that there is a Fermi surface reconstruction, right? If you ask yourself what is the real evidence that it's a spin density wave versus a charge density wave, for example, it would just be the sign of the interaction, which we have no reason to believe it's attractive. And so that's really a theoretical statement. But any Fermi surface reconstruction would reconstruct the Hall effect.
Okay, thank you.
So I just wanted to ask, how robust is the dependence of the superconducting phenomena on the angle? Is it limited to 4 to 5 degrees only, or is something like a magic angle present here as well?
Yeah, so what we have is we've measured superconductivity in a sample that's 5 degrees. We've done it a couple of times now. The reality is that in our older work, this happened at a time when none of us at Columbia had a dilution fridge, believe it or not. And Corey got a dilution fridge like a couple of years ago. And this is, so all the older samples might have all been superconducting. We just never measured it below 1 Kelvin.
Regarding what you showed in terms of the screening behavior, you explained that because the thickness of the HBN is thinner, maybe you screen better and you don't get an insulating state. But a thickness of 5 nanometers means that you screen really long-range interaction. But the belief is that the insulating state are driven by local on-site interaction. So maybe can you comment on that?
That's not clear to me in the TMDs. I think in the TMDs, at least from Andy and co-workers, the interaction is fairly long range.
But this is what determines the insulating state, long range?
Well, take for example this Wigner crystal, right?
Yeah.
The Wigner crystal is formed at sort of 1/3 density. So unless the Coulomb interaction cares about what happens 3 sites away or 2 sites away.
But the 1/3 is much weaker than the 1, right? So,
Yeah.
so obviously there are longer range interactions, but are they essential for the nu equal 1?
Yeah, that's a good question. My guess is that if you take these kinds of magnetic states, that they would indeed be important, the longer range interactions, but I'm not a theorist, so I don't know the exact details of that. There's some work by a different set of Andy's collaborators on this.
One final question from Oscar, and then we should move.
How sensitive is your insulator at nu equal to -1 to the external magnetic field, particularly if it's perpendicular?
Yeah, so that's an interesting question. So it's fairly sensitive. So by about 3 or 4 Tesla, you generally lose this insulating phase. Something interesting happens at very high field. If you go to above 20 Tesla, you have a reentrant insulator, which we believe is actually an excitonic insulator. So the Zeeman effect in these things is very strong. And so if you get to about 20 Tesla, you have an enormous Zeeman effect to the point where you almost spin polarize the carriers, but not quite. And then you can get an excitonic insulator.
Thanks.
All right, with that, let's thank Abhay for this very nice talk.